Now, let's assume we have a sorted list. Whether it's integers or something else, it is a list where the elements can be placed in increasing order. And it's probably simplest just to think about it as a list of integers. Other things will work equally well. I could certainly do linear search on a sorted list. And here, you can see a piece of code that would do it. I'm going to walk through a loop down all of the elements of the list. And if I find that the element's there, I can just return true and break out of the search. If I ever get to a point where the thing in the list is bigger than the element I'm looking for, since I assumed it was sorted in increasing order, at that point I can also break out of the list, and in that case return false, because I know it can't be in any of the rest of the list if all of those are bigger than the thing I'm looking for. If I get all the way through the list without having found it, I'll just return false because it says it's not present. Running time wise, this is actually going to be better than the brute force kind of search. I'm taking advantage of the fact that I know that in fact the element has the list has a particular order to it, but the cost is still linear. I only need to look until I get to a point where I can stop, but breaking out of that loop, as we've seen, doesn't prevent the analysis that in the worst case, this is still going to be linear. And as before, it's going to be order of the length of the list for the loop, order 1 to test if it's there or not. We've already seen that that's constant, so the overall complexity is still order n. Timing-wise, maybe a little faster, but complexity is the same class. Okay, with that in mind, now let's look at bisection search. And when I want to look at bisection search, I'm going to use that idea of dividing the problem in half. So here's the rough idea, and then we'll implement it. I'm going to pick an index in the list that divides the list roughly in half. If it's not of even length, I'm going to be close. I'm just going to pick a thing midway through. And I'm going to ask, is that element at the midpoint the thing I'm looking for? If it is, I'm done. Fantastic. If not, I'm going to ask, is the thing I'm looking at bigger or smaller than the thing I'm looking for? And depending on that answer, I either throw away the right half or the left half of the list, because I know it can only lie in one of those two sublists. And I'm going to then do the same subdivision. This is something you've seen before. It's a divide and conquer algorithm. I'm breaking this up into smaller versions of the problem, smaller lists, and in fact, I'm reducing the size of the problem in half at each step. And of course, the nice property is the answer to the smaller version is still the answer to the original problem. Once I found it, I return true. If I can't find it, I return false. Let's look at what that says about the way we would actually do the search. So if I've got a list of some size, I'm going to start off looking at the midpoint saying, is it there or not? N elements in that first version. If it isn't, let's assume that the thing I'm looking for is smaller than that midpoint. So then I look at only half the elements. And then let's assume in this case that the thing I'm looking for is bigger than the midpoint of that sublist. I'm going to look at n over 4 elements. And I'm going to keep reducing the size of the problem down by a factor of 2. So after I steps, I've got n over 2 to the I elements. And I'm done when I only got one element left. Either it's the thing I'm looking for or not. So what do I know? I know I'm going to finish looking through the list when n over 2 to the I is just 1. And by a little bit of math, that's when I is log n. Wonderful. This is logarithmic in complexity, where n is the length of the list. The characteristic, cutting down the size of the problem by a constant factor at each stage. Wonderful thing to have if we can get it. So this is really nice. It says if I've got a sorted list, I can do bisection search in log time. How would I implement it? I'll show you two examples, and one that has a different kind of cost than the other. So here's the first version of it. Again, I've got a list L. I'm looking for a particular element. The base case is if there's nothing in the list, obviously it's not there. If I've only got one element in the list, I'd simply check to see is it the thing I'm looking for and return that Boolean value. If it is, it's true. If it's not, it's false. Otherwise, what I'm going to do is find the halfway point by taking the length of the list and doing an integer divide by 2, which is going to give me out an int. And then I'm simply going to say, is the thing at the halfway point bigger than the thing I'm looking for? And if it is, I'm going to search only one half of the list. And if it isn't, I'm going to search a different half of the list. So there's a nice recursive way of solving this problem. But let's look at the complexity. That's constant. That's constant. That's great. That's constant. Also great. But that's not constant. and neither is that. And by that, I don't just mean there's a recursive call. We know that complexity. We know that's going to be logarithmic. The reason it's not constant is right there. I'm making a copy of the list. It's only half the list, but if you think about it, I'm making a copy of half the list in either case. And in the next recursive call, I'm going to make a copy of that half of the list, but that's going to add up to a larger complexity. And in fact, a complexity that's bigger than I want because of that cost of actually copying the list. What's an alternative? A very nice alternative is to say, keep the list, but just keep track of where I'm looking at. So here I'm going to set up, right here, a little helper function that's going to have two arguments. The lower half of the list I'm searching and the higher half of the list I'm searching. And what I'm going to simply do is change where those pointers go to. So let's look at it. Again, the base case down here is if I've got nothing in the list, the answer is clearly false. Otherwise, I'm going to call this helper function with the low pointer at the beginning of the list and the high pointer at the upper end of the list. And what does this now say? It says if the two pointers are at the same place, there's only one element there, I just check to see if it's the thing I'm looking for. Otherwise, I find the midpoint by taking the average of those two things. Ah, that's right. It says that's going to be halfway between low and high. If at the midpoint I have the thing I'm looking for, I return true. Otherwise, if the thing at the midpoint is bigger than what I'm looking for, then if there's nothing left to search, I just return false. Otherwise, I call it again with the same low point, but now my high point is reduced to the midpoint. I've thrown away half the things. And in the other case, I change my low point and keep the same high point. So if I were to think about it, it's as if I got my big list here. I start off with low pointing there and high pointing here. And after one recursive call, I might have low pointing there and high still pointing here. And after another recursive call, I might have high pointing there and low pointing there. But I'm cutting down half the search, but not copying the list. I'm just changing some numbers. So now if we look at the complexity here, that's not constant because of the recursive call, but within it, it is a constant amount of work. And the same thing there. So the only things I'm counting now are how many times do I do the recursive call. But the call itself does a constant amount of work. As a consequence, I've got now two algorithms. The first one has log n calls, but within each of them I have to make a copy of the list, and that's a cost of n. So overall, it's n log n. I could make it slightly tighter, but it's still going to be linear because of that copying effort. On the other hand, the second implementation simply uses the indices as the parameters. The list is never copied, and so the only cost here is, in fact, the recursive call. And that's really nice. Just to give you a sense of this, I've got two versions of those two implementations over here in my code. I'm going to run them into the machine, and I'm just going to show you that they, in fact, compute the same thing by calling bisection search. And I'm going to do the first version on a test list, and I'm going to ask if the number 9 is there, and it returns true. And I could call the same thing but ask if the number 15 is there, and it returns false. And I can do bisection search with the more efficient version. Again, I'm going to call it with 9, and it returns true. And if I call it with 15, it also returns false. And it's really hard to see in the machine the difference in timing because it's a very small list. But our complexity analysis tells us that the second solution is going to be much better than the first solution. So, what do we have here? I want to search a sorted list where the size of the problem I'm going to call n, the length of the list. Using linear search, order n. Using binary search, I can search for the element in order log n, which is great. But I had to assume that the list was sorted. So what does that say about the cost? Well, does it make sense to first sort the list and then search if I'm given a list in arbitrary order? So what that says is, well, I want to know when is it better to do sort and search rather than just search. And that basically says, well, when is the cost of sorting less than order n minus order log n? And that's when the cost of sorting is less than order n. And oh darn, that's never true. Did I just waste your time? Of course not. Because if I'm only going to do it once, it's probably not worth doing the sort and then the search. I might as well just do a linear search. I can amortize the cost. And in particular, why would I bother sorting? Well, in many cases, I might simply want to sort the list once, but then do multiple searches. I'm looking for different elements inside of this list. I just did it with my little example on my machine. And so I can amortize the cost of the sort over many searches. If I'm going to do k searches, I then want to know when is the cost of sorting plus k searches, so k times log n, when is that less than just doing k linear searches? And for large k, that sort time becomes irrelevant because it's always going to be the case that that log cost is much better than the linear cost. So it is still important to sort and then search. And that says we now need to look at, all right, how do we do the sorting?